Okay, so we are going to start day 2. I know some people are still working, but it's all right. If you notice the very first pages that I gave you the key to the first page because I wanted you to keep all your notes in one spot. So in order to do that, I know that we already did day 1 together, so I printed my key so you had it. So if you weren't here, it's kind of a gift to you. You have that now, and then flip to day 2, which looks like this. Hold on. So I gave you that key, and now we're here. This way it's all in one spot. Makes life easy for you and for me when you're trying to find your notes. So we have exponential growth and decay. So you guys talked about in physical science a little bit, growing and decaying, and now we're going to bring it back a little bit and talk about it mathematically. And then on Wednesday and Thursday, we're going to start applying it to real life situations, which can be pretty cool and pretty fun to see. At least it is for me. So we have this parent function, and that's just any type of function with a variable in the exponent, and that's why it's called exponential function. But we're going to have growth if that b value, that base right here is greater than 1. Okay, so if I have 5 to the x power, it's going to be growing. If I have 1 to the x power, well, actually we can't have 1. But if we have 1.5 to the x power, we're going to have growth. Okay, then we're going to have decay. And decay is when you're between 0 and 1. You can't have negatives for your base because you can't grow or decay negatively. Okay, that's why we can't have negative for the base. You can for A, but not for the base itself. Remember that the base is what's being raised to the exponent. Okay, so a lot of people think that this A value is that base when I ask for it, but that's the initial amount. That's where we're starting. Okay, and as you can see here on these graphs, I kind of drew them out for you. That's growing and that's decaying. You don't have to draw those in, but I wanted to show you on the side those what those meant. Okay, so when we're looking here, we're on day 2. Find it? Okay. So we have an A value and we have a B value. The B value is going to determine whether it's growing or decaying. So this value right here. This is going to tell us if we're growing or decaying. Is it greater than 1 or between 0 and 1?
Less than 1.
It's less than 1, between 0 and 1. So the base is going to be between 0 and 1, and that's why we're going to be decaying.
What was that top part? 2 words?
Growth and decay. Okay, so the question is always if it's between 0 and 1, it's going to be decaying, and then if it's bigger than 1, we're going to be growing. Now, a lot of people get this confused because they think fraction, that automatically means it's less than 1, but in the situation for B, what's our B value? What's our base of the exponent?
3.
What'd you say? Wait, hold on. Repeat. Sorry, my brain's a little off. I'm sick still.
I said 3.
Not 3. What's 4/3? Okay, so 4/3 is that base. Okay, 4/3 is the base. 4/3 is bigger than 1. How do I know that? Because the number on top is bigger than the number on the bottom. Okay, if the number is on top bigger than the one on the bottom, it's going to be greater than 1, and that's why we're going to have growth. So without even graphing, you can see which one it's going to be, growth or decay, without even looking at it. Now, here's where it gets a little tricky. When you have that negative exponent, does anyone remember what happens when we have a negative exponent? Yeah, it flips. This is
Would 1 go on top?
yes, so that's technically 2 over 1. And when you have a negative exponent, it's going to flip to 1/2.
So it'll be decay.
Yep, because B is equal to 1/2, that's going to be decay because it's less than 1. Do you have questions on any of that? Remember, you're just looking at the B value. A lot of people will look at the A value and contradict it, but it's only the base. Now let's look at this one. I have a negative exponent, which means that I do what?
What?
I flip it. So this becomes 4 over 1. That's now my B value.
Grow?
Yeah, so I'm going to be growing because it's greater than 1. Okay, so again, without even putting it into your graphing calculator, that is how you would establish that. Questions? All right, cool. So we're going to do these two here. Now you could do it without a calculator if you want to challenge yourself, or you can do it with a calculator. Either one's going to work here. Let's look at A. Are we going to grow or decay for A? We're going to grow because 3 is going to be bigger than 1. So because of the 3, it's bigger than 1, we're going to be growing in our exponential function here. Now, we can plug all of these in. I really don't care. I really just want like 3 good points. Let's see if you guys can tell me these 3 points, and then I'd be happy. I don't think you need a calculator for it, but if you need it, you can. Let's see here. If I plug in -1, 3 to the -1, what happens when I have a negative? It doesn't change to a negative.
Oh, I thought it'd be one.
It flips.
What'd you say? Yeah, it flips. It flips to 1/3. Okay, so you're saying 3 to the -1 power really is going to be 1/3. And if you put that in your calculator, you get like 0.333 something. That's the same thing as 1/3. So the negative really just flips it. Now what about 0? What's 3 to the 0 power? Anything to the
Just
0. It's not 0.
Is it 1?
It's 1. Okay, so it's really weird. It's an exponent rule. Anything to the 0 power is 1, always. Always. Okay, and then 3 to the first power is what? 3. So I don't care if you plot the rest of them, you can. You can go in your graphing calculator and you can put them in there, or any calculator, and you can get the same answers as me. Or you can just start graphing it with those 3 points. These 3 are the most crucial, in my opinion, in these types of problems. So 0, 1.
How would you graph -1 power?
So I go to the left 1, and I go up like a little bit. Not a lot, just a little bit. And then I would go 1, up 1, 2, 3. And we're going to go left to right. I know it's growing, so it's going to say growing. It's going to look like that. We're shooting up. And if you plotted the other points, you might get a more accurate graph than that. But what you're going to notice is that it doesn't go past that 0. It's called an asymptote, which we'll get back to. I know that you guys learned about it last chapter. Now let's look at this one. We have to rewrite it first. I kind of gave you a hint. The moment you have a negative exponent, we're going to rewrite it first. So I'm going to rewrite it as what to the x power? 1/3. Very good. And now let's do those 3 points that we talked about. So I have 1/3 to the -1 power. What's going to happen?
The 3 and the 1 get flipped.
Yeah, and so I'm just left with what?
3 over 1.
3 over 1, or just 3. Anything to the 0 power is what? 1. And then we have 1/3 to the 1, which is just 1/3. If you notice, okay, look at what happened. They just switched with each other. Because that's what happens when you have a negative exponent. Everything switches. So let's plot that one this time. I have -1 up 1, 2, 3, 0, 1 still, and then 1/3 is about right there. And now we're going to be decaying, which means we're going to be going down. We're going to be going down. It's a bad graph, but going down, decaying. Hey. Compare the two graphs. What does the negative exponent do to the graph? What happened to the graph, not to the function, but what happened to the graph? Yeah, so it switched. It's called reflection. Okay, so we talked about reflection over the x-axis. Now we're going to be reflecting over the y. So if I drew in my highlighter here, if you notice, they're opposite of each other. This flipped to here, this flipped to here. They are reflecting over the y-axis. That's what happened. Notice that both graphs get closer to x but never touch it. This means you have a horizontal asymptote at y equals some number. Where does it never touch but get really close to? Yeah, so 0. That's called an asymptote from like Chapter 9, I believe, is when we started talking about asymptotes, where it gets really, really, really close to something but never touches it. So it's a line which the graph gets close to but never crosses. I just want to refresh your memory here. We've already learned what an asymptote is, but I want to refresh your memory. You can flip when you're done, so I know you're ready. See, this is a chart. It's very quick. Let's talk about both of them. Left to right, when you look at both of them, here's your growth function, here's your decay function. Are all x values good? Do I go forever left and go forever right?
Yes.
Yeah, so the domain for both of them is all real numbers, or negative infinity to positive. Okay, that's true for all exponential functions, just like it was for all quadratic functions and all polynomial functions. Those were all real numbers for your domain. We could put in any x value. Now the range is top to bottom. Sorry, bottom to top. Oof. For both of them, look. I can put my pen here to represent both of them. Where do I start?
Mm, 0.
0. See that? My function starts at 0 and it goes on where? To infinity. Range is one of the most incorrect answers that we see. So we're starting at 0 and we're going to infinity for both of them. And we're not including 0 because it's an asymptote. It doesn't touch it. We already talked about our asymptote for both of them. It's y equals 0. And you can make a little bit of a correlation here. Wherever your asymptote is where your range is going to either start or end. Bless you. Okay, so wherever your asymptote is where your range will start or end. Always. Your intercept. Both of them have a y-intercept. Where was it? 0 comma what? 1. Very good. 0, 1. So 0 comma 1. They both did. Now here's where it's a little different for both of these. Now, end behavior, going back, way back when. It always represents your domain and your range in one statement. That's really what end behavior, these limit statements are saying. What is your domain and range? When you look at these, it's representing your domain. You take a look here. Negative, infinity, and positive. They're represented here. That's your domain. Okay, it's cool how it represents both of them just in one saying. Your domain will always be represented here. So as x is going to negative and x is going to positive. Now your range is kind of what you're going to be filling in here. Because watch, as x is going towards negative infinity, here it is going towards negative infinity, where is the function approaching? It's
0.
the y value is 0. Very good. And when we do the opposite, as x is going to positive, the function's shooting up to where? Infinity. Very good. And now look at the correlation. I told you that the range would be represented, and it is. It's really cool how that plays out. Your domain is represented as x is going to these values. The range is represented by what we write in those blanks there.
And it's going to be similar for decay.
It is going to be similar for decay. Now, the only difference is going to be a little bit, it's going to be switched a little bit, and here's why. Because here, as x is going to negative, here it is, where's the function going? Is it going to negative? Positive. Okay, it's going to positive. The y values are going to positive infinity. And then as x is going to positive, it's going to 0 right here. Very good. And again, you can see that our domain and our range are represented. Here's a 0, and here's the infinity. Okay, it's not going to be in the exact order, but you should have the range in those two values. That's the cool part. Now, for the interval of increase and decrease, am I always increasing or decreasing in growth? Increasing. So I'm going to be increasing, and it's always going to be your domain, negative infinity to positive. So what that means is you're always increasing. That's what you're saying. For all real numbers, for negative infinity to positive, I'm always increasing. What about decay?
Decrease.
And am I always going to be decreasing, or was there a part where I stopped?
0.
Yes, I did stop at 0. I totally understand that. But yes, it kept going on 0, and that's the y value. And it's actually, when you're talking about increase and decrease, you're talking about your x values. So I'm always decreasing forever and forever and forever, and that's why it's negative to positive. And that's how it is